is useful. Useful for synthesizing drugs, useful for understanding biology, just really useful. So let's take a look at the 5 reactions I'm going to ask you to know in this chapter. If you could just memorize these 5 transformations here, you're halfway there. I'm going to show you these 5 reactions in this chapter, and then I'm going to show you a bunch of exceptions, which is really what creates all the work. It's the exceptions that create all the work. And then I'll show you a few functional group transformations, some things you can do with these side chains that'll make that useful. Let me try to make sure this is focused here. Sorry. Okay, here's our 5 reactions. This is your main challenge. Get out of here today and make sure you memorize these reactions today. They're not that hard. But let's take a look. I'll take a little preview here of our secret recipes. And then after I show you these, we'll walk through each one of them one at a time so you can see how these reactions work. Okay, so I'm going to start off with this bromination reaction. If I simply treated a benzene ring with Br2, I already told you nothing happens. You don't brominate across the double bonds of benzene rings. They're unreactive. But I can add a special catalyst to this reaction. And the catalyst is FeBr3. And you've never seen that before. It's a Lewis acid. It's going to activate that bromine and turn it into a super aggressive electrophile. And it still doesn't add bromine across the double bonds of benzene ring. It substitutes that hydrogen atom. And nowhere on my exam am I going to be so kind as to draw that hydrogen atom for you. I expect you to recognize that there are hydrogen atoms attached to benzene rings. I'm just doing that on this slide here so you can see more clearly that something was substituted. And it's not an electronegative leaving group. Okay, here's our next recipe. The next recipe is to use nitric acid, HNO3. That's nitric acid. But you know, nitric acid is actually a strong acid. Kind of scary because it's a strong acid and it's oxidizing. It's still not strong enough. So they add an acid catalyst to this, something even more powerful than nitric acid. They add sulfuric acid. So that's the 2-part recipe you need in order to nitrate a benzene ring. So this is what you do. Okay, so our third reaction in this list is to take a functional group that you haven't seen before, but you're going to see a lot of, and it's called an acid chloride. So I've got a chloride here. You can kind of tell that's going to be a leaving group. So it looks kind of like a carboxylic acid, except where there used to be an OH, there's a chloride. So this is a new functional group for you, and you are going to use acid chlorides very heavily in Chem 51C. That's going to be your money reagent in Chem 51C, and we're giving you sort of a preview of how useful that reagent could be. And once again, we need a Lewis acid, and the Lewis acid we use is not this iron Lewis acid, it's aluminum trichloride. So aluminum is also a very powerful Lewis acid that's going to initiate the reaction. So acid chloride plus aluminum trichloride, and that allows you to substitute hydrogen atoms with carbon-carbon bonds. Very powerful stuff. Okay, so this 4th reaction, reaction number 4, we're going to take sulfur trioxide. You might have heard this term acid rain. I don't know if that's such a common term. If you burn coal that has sulfur in it, the skies fill with sulfur trioxide, and when it rains, that turns into sulfuric acid. So that's not very good, of course. It causes buildings made out of stone to slowly degrade. Acid rain is a big problem. But here we use this sulfur trioxide reagent in combination with sulfuric acid. And that's a powerful way for making carbon-sulfur bonds. So look at all the different heteroatoms. Up here I show you how to make carbon-halogen bonds. In reaction 2 I show you how to make carbon-nitrogen bonds. In reaction 3 I show you how to make carbon-carbon bonds. In reaction 4 I show you how to make carbon-sulfur bonds. And the 5th reaction here is to take a different kind of halide, and it doesn't really matter what the halide is, I'll just take Br, and directly attach it to an alkane. Not a carbonyl group, but just an alkane. Ethyl, isopropyl, cyclohexyl. So no carbonyl attached there. And it can be a chloride if you want. We'll talk more about this. And once again, we use the same Lewis acid, aluminum trichloride. Maybe it bothers you that it's not aluminum tribromide. That would work too. It's just that's a more expensive reagent. Okay, here's our 5 reactions. Now let me be straight with you here. They're not all equally useful. There's 3 reactions here that are going to be much more useful for the Chem 51 series, and that's reactions 1 through 3. So these are the most useful of these transformations. What you'll find is that carbon-sulfur bonds, at reaction number 4, Well, there's just not that many things extra that we're going to show you how to do with that. It turned out to be important historically, and there's some important aspects to that, but there's just not as many important things that you can do with that. And then this last reaction, reaction number 5, has so many exceptions to it. Exception number 1 that I'll talk about later is that you have to use this in excess. Here's my symbol for excess. And I'm going to show you all kinds of reasons why that's got exceptions to the reaction. It only works in this special case, and it's not really efficient, and so we'll be kind of tired of that reaction because of all the problems with it. Okay, get out of here and go memorize these 5 transformations. I promise you, some combinations of these will be on every single final exam in Chem 51B in every section this quarter. These are important transformations for organic synthesis. Okay, let's talk about the mechanism for all 5 of these reactions. They all go through the same mechanism. All of them go through the same mechanism. And so I'm going to give you this mechanism, and it's a 2-step mechanism. There's no way to replace an H atom on a benzene ring through a 1-step mechanism. So let me go ahead and start off my mechanism, and I'm going to use this generic symbol, once again, E+, as a way to symbolize some sort of an electrophile that's really, really hungry for electron density, that's much more electrophilic than anything you saw back in chapter 10 or 11, more electrophilic than Br2 or chlorine or HBr or borane. So I'm going to show you these 5 secret recipes and it's kind of bothering me, so I want to draw this H atom, because I'd like to keep my eye on that H atom we're going to substitute, just to remind myself that even if I didn't draw that, there is an atom that's being replaced, or replacing that H atom. Okay, the arrow pushing involves the pi electrons of benzene. Right? These are way less reactive than a regular pi bond. All those pi electrons are so happy, they're part of a 6-electron aromatic ring system. But if your electrophile is aggressive enough, they can react with one of the pi bonds in the benzene ring. So I'm going to show that pi bond attacking. This is very slow. This is the slow step in the mechanism because you disrupt aromaticity. And so when I draw this intermediate, it's going to be a carbocation. So I'll go ahead and draw this H atom just poised right there. And you have to draw that H atom, because every time you're going to use that H atom in the next step. We don't always draw H atoms in organic chemistry when we use these structural drawings. Here's my carbocation. I took electrons away from that carbon. So it looks kind of like a secondary carbocation, but it's not a secondary carbocation. Really, it's allylic. It's got all this resonance stabilization there. And we have a special name for this kind of carbocation that arises from addition of electrophiles to benzene rings. When you have a 6-membered ring like this and a carbocation and those double bonds, we call these intermediates in these electrophilic aromatic substitutions, we call these arenium ions. So this class of aromatic ring substrates we call arenes. So a benzene ring is what I would call an arene. It's an aromatic alkene. And this ion is an arenium ion. So really that's not plural, so forget the plural there. Okay, that's an arenium ion. So every single one of those 5 recipes that I showed you is occurring under acidic conditions. So there's acidic reagents in there, and that means there's also counterions floating around that have lone pairs. Things with minus charges that aren't really very basic. So I'm going to draw this. This is my symbol. This A minus is my symbol for the conjugate base derived from some sort of an acid. And you don't need anything basic to pluck this proton off. See that proton that I've got dangling out there saying, hey, grab me? This proton wants to leave, because as soon as we pluck this proton off, anything can pull that proton off. We get back aromaticity. Oh my God, that is so good. That just feels so good. And now this system that was all frustrated here gets to be really happy, because now it's back to an aromatic ring system. So aromaticity is a huge driving force in these electrophilic aromatic substitutions. They make it very hard to do the first step in this reaction. Right, this first step is slow because you lose aromaticity, and I'll just write slow here. But this second step is really fast because it wants to regain aromaticity. Right? That was really pissed off there when it was an rhenium ion, and we got to fix that. Okay, so I want to talk about resonance in this rhenium ion. I hope you can see there's going to be all kinds of resonance structures that we can draw here. And so I want to take the time to draw out, in this one case here, in this very general case, all of the different resonance structures that we can draw for this rhenium ion. And you need to get ready to be drawing bunches of resonance structures for rhenium ions. This chapter is going to be filled with that. This is exactly the kind of stuff that they ask you on standardized exams for entrance to professional schools. They really seem to harp on this rhenium ion business. So let me draw this positive charge here. And the first thing that I want you to do is I want you to resist the temptation. And you will have this huge temptation because this harkens back to your understanding of all the stuff that we've covered in the previous chapters. I want you to not do this. Don't take your A- or anything negatively charged and attack that carbocation, right? Gee, it sure does look like it wants to be attacked. I thought carbocations, don't things always attack carbocations? No! If you attack that carbocation, you'll never get back aromaticity. Do not use A- to add to the carbocation. Right? Don't take Br- and add there. If you add HX across a double bond of a benzene ring, you've lost aromaticity. You've lost 36 kilocalories per mole of aromatic resonance stabilization. Okay, so let's talk about resonance stabilization in this carbocation. What I'm going to do is I'm going to draw one of the resonance structures. I'm going to swing this pi bond over here and move that double bond to satisfy the carbocation. And when I do that, this next resonance structure that I draw will have the carbocation in a different place. So I'll draw my H and my E in the same place. And here I just shifted that double bond over. And here's that other pi bond, it's still there. And now my carbocation is there. And of course, if I had a substituent at that position that stabilizes carbocations, that would be pretty sweet, that resonance structure. But of course, I don't have a substituent at that center now. I don't have a substituent down here on the carbocation on this structure. Okay, and now let's swing over this other pi bond, draw another resonance structure. And here's my third rhenium ion resonance structure. And you need to be good at seeing rhenium ion resonance structures and depicting them by drawing them. And I fully expect you to be good at drawing rhenium ions because of practice. Okay, so these are our three rhenium ion resonance structures at a minimum that I can draw. There may be other resonance structures if I've got substituents next to the carbocations. So avoid the temptation to make nucleophiles attack rhenium ions to make sigma bonds. That never happens. A- or Br-, nothing will ever attack that carbocation. The only thing that happens in these cases is that something will pluck the proton off to help regain aromaticity. Okay, so all five of those reactions that I showed you, bromination, Friedel-Crafts acylation, the one where you form a carbon-carbon bond, nitration reactions, sulfation, they all go through this two-step mechanism. You add an electrophile that adds to a benzene ring, and you lose aromaticity and make this frustrated rhenium ion, and then something plucks the proton off to regenerate aromaticity. And the only thing that's going to change throughout these three mechanisms is what's that electrophile. So I'm getting ready to show you all these recipes, how you generate super powerful electrophiles, and then it goes through this same two-step mechanism. So let's start off with halogenation. Okay, so this is the halogenation recipe that I showed you, and as I'm indicating up here, you could do the same reaction with FeCl3 and chlorine Cl2. Right? If you don't like having a carbon-bromine bond, you can make a carbon-chlorine bond on a benzene ring. If I ask you how to put a chlorine on the benzene ring, then just write Cl2 and FeCl3, and the reaction will work the same way, equally efficiently. Now, if you're doing synthesis, there's no reason why carbon-bromine bonds on a benzene ring are better than carbon-chlorine bonds. Why are you learning this reaction? You can't do SN2 reactions with aryl bromides. That carbon-bromine bond in the product, you can't do SN2, you can't do SN1. Why on earth would the book show you this, and why would I tell you that this is a useful reaction? And the reason why this reaction is going to be useful won't be apparent until Chem 51C. In chapter 20, I'm going to show you, well, somebody will show you a secret reaction in Chem 51C that converts that carbon-bromine bond into a super powerful nucleophile. More powerful than any nucleophile you have ever seen. More powerful than alkoxide nucleophiles, more powerful than alkynyl anion nucleophiles, more powerful than amides. That bond right there is a super nucleophile. And really, that's the essence of Chem 51C. Did I just go off the side there? Let me Okay, so that's why I'm showing you this, and it's not going to be that useful until, you just have to wait until Chem 51C, and you're going to be using that all over the place. Everywhere you put a carbon-bromine bond or a carbon-chlorine bond, you're going to be able to convert those bonds into nucleophilic bonds. Go from leaving group to nucleophile with that super secret reaction. It's not a big secret. You add magnesium to it, but whatever. Okay, so let's talk about the mechanism. I said all of these things involve the same two-step mechanism, and the only thing that changes here is how we generate the electrophile. And that's what makes these mechanisms look intimidating and complex. So let's start off with this. Let's go ahead and draw molecular bromine. That's one of the reagents. And I'm just going to draw one of the lone pairs. I'm not going to fill in all the lone pairs on the halogen atoms. You can do that later. What I want to do is I want to focus on what's the role of this FeBr3. It's a Lewis acid. That iron is very unhappy. That iron has electronegative atoms all over it. Let me draw those. Here's one of the electronegative atoms. Here's the other electronegative atom. Here's the other electronegative atom. I'm running out of room, but that's a bromine on top. Boy, that iron really would love another pair of electrons. If only there were some place where it could find another pair of electrons. Just some place. Gee, where can it find... Oh, look at that. This is what's surprising. I don't know if you've ever seen anything. Now, you've seen oxygen atoms with lone pairs interact with Lewis acids. Zinc chloride activated oxygen when ZnCl2 converted OH to chloride. So this is something that's new to you, this Lewis acid concept with halogens. And we're going to see that, I guess, 3 times. We got 5 reactions to show you. 3 of them involve this kind of Lewis acid activation. Okay, so now we have this very weird looking. Well, this is really going to freak you out because you've never seen anything like this before. But look at this, I've got 2 bonds to bromine before. You've seen that. We had cyclic bromonium ions in 3-membered rings. Whenever you have 2 bonds to a halogen, you have to have a positive charge on that halogen. Right? You can't just have 2 bonds to halogen without having a charge. So let's put the positive charge there. And yes, there's lone pairs on that bromine, but here, I'll draw the rest of this so we can see how things fill out. Okay, that bromine still has 3 lone pairs. Who cares about that? That bromine there has 2 lone pairs, but it's got this positive charge. And here's this iron atom. If I put a positive charge on bromine, I have to have a negative charge somewhere in my molecule. And that negative charge appears here. It's the iron that carries the negative charge. I would call that a ferrate. Anything with a negative charge has an 8 ending. So that would be called a ferrate species. The point here is that by binding iron to bromine, I've converted this bromine into a super leaving group. This whole, let me circle it. This entire thingamabob right here, this thing, is now a super powerful leaving group. Super leaving group. More powerful than anything you've seen before. Super fantastically powerful. It's going to make it exceptionally easy for anything to attack this bromine and displace that whole FeBr4 piece of junk there. Okay, so let's draw out our 2-step electrophilic aromatic substitution reaction. I told you they all involve the same mechanism. All we're changing is the electrophile. And so now I've shown you this secret electrophile, this FeBr, and I'm not going to redraw the structure. I'm just going to write FeBr3 here. Minus charge there, but I'm going to get the charges right. That's essential. So here's my FeBr4 leaving group. I've got that iron with those 4 bromines, and it is really happy with that. And so now I'm going to take my pi electrons in the benzene ring, and I'm going to do an SN2-like reaction on that bromine atom. And I'm going to break this bromine-bromine bond. Now that I've got this super fantastic leaving group, even a pathetic pi bond in a benzene ring is good enough to attack that bromine and displace this leaving group. That's how good that leaving group is. Even a benzene ring pi bond can displace that. So now let's draw out the next intermediate in our mechanism. I'm going to have a carbon-bromine bond in my next intermediate. And there was a hydrogen atom here that I didn't draw. Right? If you draw this carbocation, this rhenium ion intermediate like this, you're screwed. You're screwed. The most important thing you could do on your substrate is to the most important thing is you can see the hydrogen atoms that are not drawn. But if you're not good at seeing things that aren't drawn, then draw them in. Because you need that hydrogen atom here. You need that proton. You're going to pluck that off in step 2. In every one of these mechanisms for the 5 reactions we learned in this chapter. So you need to know that that proton is there because we're getting ready to pull that off. Now, anything can pull that atom off. I'm going to redraw this ferrate species. It's got lone pairs on all of the bromine atoms, and I'm just going to draw one of the lone pairs on one bromine atom. And this is going to seem weird to you. Basically what I'm telling you is anything with a lone pair could pull that off now. But this is of the species that are floating around in your solution, this is the species that's most likely to pull that proton off. So that lone pair plucks off the proton. Now we're aromatic again. That's what that rhenium ion wanted, is to become, and I'm not going to draw all the resonance structures here, but there may be cases where you have to draw all those resonance structures of that rhenium ion to understand the chemical reactivity. And look at that, we've made this fantastically useful carbon-bromine bond, not useful this quarter, but useful next quarter. And you will use that over and over and over in 51C. Total money reaction there, the idea that you can put a bromine atom or a chlorine atom on a benzene ring. Okay, so it's just a 2-step mechanism, and it looks really complex with all this iron and bromine, but if you could just focus in on this idea that it's 2 steps every time, I think it will make things a lot easier. Okay, let's talk about forming carbon-nitrogen bonds. Nitration reactions. So remember our 2-step recipe, and I used to find this really hard to keep straight when I was an undergraduate. It's like nitric acid, they're both acids. Nitric acid, sulfuric acid, what acid is doing what? The reagent is nitric acid. There are some types of benzene rings, not just simple benzene, that are so reactive you don't need an extra acid. But in most cases, you should always add sulfuric acid when you write this recipe out. Just assume you have to add a super duper duper powerful acid like sulfuric acid. Sulfuric acid is way more powerful as a proton donor than nitric acid. Okay, so always include these reagents. So why would you put a nitro group on a benzene ring? So I'll draw the complete resonance structure for this nitro group. It's got all these lone pairs on the oxygen. There's another resonance structure I could draw that puts the O- on top. I'm not going to draw that. Okay, why would you care about this? There's no reason to have a nitro group on a benzene ring. The only reason people put nitro groups on benzene rings is so they can reduce them to amino groups. That's the only reason. So nitro groups are useless. And later in this chapter, I'll show you a secret reaction, yet another secret reaction that converts nitros, which are useless, into something useful, into an amino group. So this is aniline. And anilines are super important. If you go look at the top $20 billion selling drug list for pharmaceuticals in the United States, over half of them will have anilines in them. So this type of carbon nitro bond, not nitro groups, but anilines. So, and the secret recipe is this. I'll just tell you. Hydrogen and palladium on carbon. It's the same recipe you use to hydrogenate double bonds. Who would have thought that? Who would have thought that the conditions you use to hydrogenate double bonds can burn off all those oxygens and leave you with an NH2 group? And that is a very powerful sequence, this sequence where you nitrate and then reduce. Okay, so that's why I'm showing you how to put nitro groups on there, is so you can convert them to amino groups. And in chapter 25, which is the chapter on amines, you're going to come back and use this reaction over and over and over. The book is gambling on the fact that you're going to forget this two-step sequence, but I think you're going to remember it when chapter 25 rolls around. Okay, let's talk about the mechanism for this reaction, and I'm going to start off by symbolizing my sulfuric acid as HA. I'll draw it backwards there. So that's the sulfuric acid. This is, you need a powerful acid catalyst when you do these nitration reactions. So let me draw the Lewis structure for nitric acid. Here it is. So the N has a positive charge. Whenever you have 4 bonds to nitrogen, there's going to be a positive charge. If you just have 1 bond to oxygen, it's going to have a negative charge. Okay, in a million years I would never have guessed this, and I don't think you would have either. The first step in this mechanism is hard to figure out. If you have not practiced this, you won't be able to figure this out. Because you will irresistibly be drawn to use the lone pairs on this oxygen to pull off a proton from your acid. Right? O minus, that should be pulling the proton off the acid. Actually, that happens. 99 times out of 100, this O minus lone pair pulls off the proton from the acid. But that 1 time out of 100, when this lone pair pulls off the proton from the acid, it converts the OH into a water leaving group. So you're not crazy if you think the lone pairs on the O minus will pull off the proton, but it's just going to get pulled right back off the oxygen. So it'll protonate O minus back and forth, and eventually this OH oxygen will get protonated. And now let's take a look at that leaving group. There's the water leaving group. You can see that's now a leaving group. You've seen that before, water leaving groups. And here's the rest of this molecule. Now let me draw a lone pair here on that oxygen. And I've got 3 bonds to oxygen. That has to have a positive charge. Now this looks really ugly. Oh man. Having 2 positive charges. Don't ever do this again. Don't ever again draw a structure in organic chemistry. You will never again in organic chemistry see a structure where there are 2 positive charges next to each other on a Lewis structure. This is the only case. So next time you're thinking, oh, I've seen that, but don't try to duplicate this on any other mechanism. Because I'll say, oh, you're crazy for putting 2 charges, positive charges next to each other. If you do a quick calculation with Coulomb's law, you'll figure out that this is, well, actually, there's other resonance structures that will help you understand why this is a special case. But I just don't want you to be comfortable drawing 2 positive charges next to each other on neighboring atoms. What I want you to see here is that this leaving group is now so fantastic that you can now push out that leaving group, water, and there you go, you've lost water. And what it will give you is this intermediate that you've never seen before. I'm not going to draw the water leaving group. What I'm going to draw for you is this spectacularly electron deficient electrophile called a nitronium ion. So this is a nitronium ion. You've never seen it before. I hope you can see, oh my gosh, that nitrogen, everything's electronegative. They're all fighting each other. Unsuccessfully, they're fighting each other to see who gets the electrons. So you've never seen this nitronium ion before. That's new stuff. And super aggressive electrophile. And so reactive, it would nitrate your mama if she crawled into this reaction. Very, very reactive electrophile. Your mama won't crawl in the reaction, but it... Let's draw this nitronium ion. There we go. So you know what's going to happen. It's the same 2-step mechanism. Now it's kind of boring. Okay, we're going to take this pi electron. Okay, we've got our electrophile, which sometimes we symbolize as E. Oh, let me use a red pen here, because I just like to use red pens for my arrow pushing. We've got this pi bond is going to attack our electrophile. I don't want to make a 5th bond to nitrogen, so I better break one of these bonds. I'll arbitrarily break the bond on the bottom. So there, we've made our carbon-nitrogen bond, and we've generated our rhenium ion intermediate. We've disrupted aromaticity. So we made the nitrogen happy, but the benzene ring is kind of sad because it lost aromaticity. And here's our nitro group on there now. There it is. There's always a positive charge if there's 4 bonds to nitrogen. There's my O minus. And I'm so smart, I'm not going to forget to draw that proton in. Remember, if you do that, you're in trouble if you forget to draw that in. In fact, I like to draw it in on the starting material just to make sure I don't forget to draw it in on the rhenium ion intermediate. I don't have to draw that in on the starting material. It just helps me to make sure I don't forget when I reach this stage. Okay, so here's this rhenium cation positive charge. So we've lost aromaticity, very stressed out, and anything can pull this proton off. The water can pull the proton off, nitrate anions can pull this proton off. I'm just going to symbolize this anionic species here by drawing A-. We don't need to be particular about what species is pulling the proton off in this reaction. So I tap that proton, and now the electrons go back to the benzene ring, and it regains aromaticity. Step 2, done. So really the only difference here is just how I generated my electrophile. In the previous reaction it was this very weird looking FeBr4 attached to bromine. Here our electrophile is a nitronium ion, and I'm not going to draw the structure for that's a substituent, I'll just draw NO2. Okay, so that's nitration, that's forming carbon-nitrogen bonds on benzene rings. And so I told you that there were 3 more useful reactions and 2 of them that were less useful. And I'm going to cover these in the order the book covers them. Right, I gave you 5 reactions, 1, 2, 3, 4, 5, and I'm going to skip ahead now to reaction number 5. So just to be clear, I don't think this is the most useful reaction. I can't imagine you're going to see this reaction after chapter 18. Probably not. But here's a couple of reasons why it's important historically. What you may or may not remember that we talked about the use of toluene sulfonic acid, TSOH, or sometimes abbreviated PTSOH, paratoluene sulfonic acid. Chemists use that when they want a solid acid. Sulfuric acid is inconvenient because you have to measure out a liquid. It's not easy to generate to weigh out 2 microliters of a liquid, but toluene sulfonic acid is kind of like an organic version of sulfuric acid, and it's a solid. You can weigh out a couple of crystals of that. It's very convenient, and this is how you make it. You do this secret recipe for forming carbon-sulfur bonds. Sulfur trioxide, that's the stuff from acid rain. And you use, once again, we're using sulfuric acid as a catalyst for this reaction. Just like we use sulfuric acid as a catalyst for nitration. Why do so many textbooks talk about sulfation? Because the first class of synthetic antibiotics that were ever produced by organic chemists had these types of sulfonyl groups in them. They were called sulfa drugs. They were very popular. So penicillin was developed, and then organic chemists wanted to synthesize their own powerful drugs. And they realized that all these dye molecules, red dye number 2, red dye number 4, often tend to bind selectively to one kind of cell and not another. So they tried modifying those, and they found that when they put these functional groups on there, that these killed bacteria faster than they killed human cells. And those drugs are called sulfa drugs. And that's why textbooks 80 years later are still emphasizing this reaction. And it's got some importance, but it's not the importance it used to have 50 years ago. Let's talk about how you generate E+. It's the same kind of 2-step mechanism. And again, what varies here is how we generate E+. So here's sulfur trioxide. It's a planar molecule, actually pleasingly planar and symmetrical. The geometry doesn't matter, just thought I'd mention that. And when you put this in the presence of sulfuric acid, I'm going to symbolize the sulfuric acid like this, like HA. And what we're going to do is we're going to protonate sulfur trioxide. It will go from being a powerful electrophile to being a really powerful electrophile. Now, I could draw a protonation of a lone pair, and what I'm instead going to do is I'm going to show this pi bond attacking the proton. Gives you the exact same intermediate. It'll just give you a resonance structure of what you would have gotten if you used the lone pair. When I use the pi bond to attack that proton, and the proton will go on oxygen, you can more clearly see why sulfur becomes such a powerful electrophile. Remember, the sulfur is not a second row atom. There's no octet rule with sulfur, right? You can easily have, as in sulfur trioxide, you can easily have 6 bonds to sulfur. That's actually pretty common. So don't worry about the fact there's 6 bonds to sulfur. It's not a second row atom, it's a third row atom. Okay, so here's this protonated sulfur trioxide, and that is now a really aggressive electrophile. And I think the rest of this is pretty obvious. It's that same two-step mechanism. Okay, we have these pi bonds that are part of a benzene ring. And I'm not going to redraw this whole structure because I don't think I have enough room, so I'll just symbolize it like this. But you can see why electrophiles might want to attack that sulfur atom. If I ask you to draw the mechanism, I would expect you to draw this whole Lewis structure here. There we go. We form a carbon-sulfur bond. And so now when I draw this intermediate, it's that same type of rhenium ion. Let's draw that rhenium ion. Here it is. And this time I'll draw out that whole sulfonyl, sulfonic acid type group. And I guess I didn't mention that, but this class of compounds is called a sulfonic acid. You may not remember that TSOH stands for paratoluene sulfonic acid, but that's the name of that functional group. It's a sulfonic acid. Okay, so I spent all this time drawing this sulfonic acid residue down here. Oh, it's exhausting. Oh, but if you're so exhausted that you forget to draw that proton, you're going to be in trouble. Because you need that now. You need to show how we are ever going to regain aromaticity. And I can't resist drawing this proton here in the starting material because that helps me keep an eye on what gets substituted. You don't have to, but I like to do that. And then something present in your solution, and we don't have to be particular about what, pulls this proton off and allows this system to regain aromaticity. There we go. So now we're back to an aromatic ring system. And there's our sulfonic acid product. So that's how you make carbon-sulfur bonds. And again, this is reaction number 4. It's not as powerful as reactions number 1 through 3, but the book covers that sort of third in this sequence of reactions that it covers. Okay, let's step back and talk about reaction number 3, the third reaction that I showed you. Very powerful reaction, and one of the most useful of those 5 reactions that I showed you because it makes carbon-carbon bonds. And every organic chemist, myself, Professor Freeman, Professor King, Professor Guan, we love to make carbon-carbon bonds. So here's our recipe. Remember, this is that recipe I showed you. You take some sort of a benzene ring, you take this species called an acid chloride, which I said you're going to see a lot of this in Chem 51C. That's the acid chloride. There it is. And you take this Lewis acid, aluminum trichloride. Looks a little bit like FeBr3, and in fact it does the same kind of stuff. So let's go ahead and draw out this this mechanism here. Let me take the acid chloride. And I'll draw the lone pairs on chlorine. Now, there are lone pairs on oxygen. Every fiber of my being wants to use the oxygen lone pairs to attack aluminum trichloride. Because I know that aluminum trichloride loves oxygen. I know that aluminum loves oxygen in general. And in fact, the lone pairs of oxygen do attack aluminum, but they come right back off. Oxygen attacks aluminum, it pops back off. Oxygen attacks aluminum, it pops back off. Every once in a while, this chlorine lone pair will attack aluminum. And what it does is it converts that chlorine into a super powerful leaving group. So now let me draw this species, this very angry looking species here. Here's all these bonds. Look how confusing and complex that is. Now if I've got 2 bonds to a halogen, I have to have a positive charge on there. So let me draw my positive charge. There it is. And I have to have a negative charge somewhere. Well, I just added more electrons to aluminum. That picks up the negative charge. So I would call that an aluminate. If somebody said, what's that thing? I'd say, oh, that's an aluminate. That tells you aluminum with a negative charge. The point here is that we've just created a very powerful leaving group. See this whole thing here? That's a leaving group. And it is super powerful. And it is such a powerful leaving group that these lone pairs over here on oxygen can now bend over and push out. this tetrachloroaluminate anion. And when we do that, we generate our key electrophile, an acylium ion. This is called an acylium ion. And you've never seen anything like that before. Let me just put a little label here. See that thing right there? That's an acylium ion. It's like, what is that? What on earth is this acylium ion thing? Well, what is that about? Let me draw the lone pair in there. I know it looks really freaky to you, and I'll draw the lone pair with the tetrachloroaluminate just so we can see it. Here's aluminum. It's tetrahedral, but I don't think I have enough room to show that. That's the counter ion. What's that acylium ion? An acylium ion is more stable than a T-butyl carbocation. Now, you're totally familiar with drawing tertiary carbocations. This acylium ion is more stable than a tertiary carbocation. And the reason is, both oxygen and carbon have filled octets. That's intrinsically more stable than a T-butyl carbocation. So it may look freaky to you because I drew a resonance structure with a positive charge on oxygen, but at least oxygen has 8 electrons, and at least carbon has 8 electrons. So don't get too freaked out by that acylium ion. Okay, that's how we generate an electrophile. This is called a Friedel-Crafts reaction. In the early days, this is one of the most powerful reactions for making benzene ring derivatives. And we now have a new set in organic synthesis. I don't think we'll have a chance to teach you about those in the Chem 51 series. We now have new sets of reactions for making bonds to benzene rings. But for decades, this was the only reaction we had. So I'm going to draw this acylium ion. It is very electrophilic, even though it's more stable than a T-butyl carbocation. It's still very electrophilic, and so electrophilic that simple benzene rings will attack it. So let's go ahead and draw our standard mechanism. We attack something. Of course, I'm not going to attack the oxygen atom. Who would attack the atom with the positive charge? We attack carbon. And if you wanted to understand why you attack carbon, draw the resonance structure of an acylium ion. Okay, so here's our intermediate, rhenium ion. It has now lost aromaticity. We now have a ketone group on here. Wow, that's convenient. Chem 51C will focus on carbonyl groups, just like biology focuses on carbonyl groups. Okay, and we're not, notice I didn't forget to draw in that proton on my rhenium ion. There's my positive charge. And so now on our last step, some sort of a Lewis acid. It's actually this tetrachloroaluminate, but we don't have to be really particular about that. Anything can pull that proton off. It is so easy to pluck that proton off. Look at that. Oh yeah. That just feels so good. And so now we've regained aromaticity and we've formed a carbon-carbon bond. Okay, so that's the 4 of our 5 reactions that we're learning about electrophilic aromatic substitution. So when we come back, I'm going to show you how to do this 5th version. It's actually another Friedel-Crafts type reaction. Not quite as useful. And then we'll just talk about a whole lot of exceptions to these reactions. So get out of here and practice those.